the hypothesis, and we want to talk about the hypothesis and the evaluation. The evaluation is the conclusion. The reason I call it evaluation, because in your conclusion you are evaluating your hypothesis. So this is at the end of the report, and this is where you return to your hypothesis and you draw a conclusion about the hypothesis. So that's called the evaluation. And so I'm going to pair these two. So let's take an example. An example of a hypothesis for this lab would be the relationship. So it can simply be a statement. The hypothesis can just be a statement. It does not have to be an argument. It doesn't have to tell me why you think this, because maybe you just made a random guess, and that's okay. It is something like this: the relationship, and we're talking about mathematical relationship, between mass and volume of this metal, whichever you had, is linear. So that might be your hypothesis. Now that's actually not complete, but I'm going to show you why in a second. We started to talk about this in the context of uncertainty. Let's say I've got mass and volume like this, and I find something like this with my data. Your hypothesis was that the relationship would be linear. So then you plot your data, you collect all your data, you plot it, and now you have to say whether your hypothesis was right or not. So you're going to test it. What am I going to conclude in this case? That it's not linear? Okay, why would you say that, Michael? Because what? Okay, so it'd be like this. So maybe there's actually 3 lines. A trend line? What if I did the thing where you go through the middle? What do we call that? Trend line or best fit line, right? So what if I did this? Is that linear? Well, the line's linear, obviously. Do the data fall on that line? So it's not linear? Do the data fit the hypothesis? No? Why do you say no, Stephen?
I don't think it's linear because you can't plot all the points in the same line.
So you can't plot all the points in the same line. Yeah. Maya? What's that? What about uncertainty? What do you mean? Okay, so what if the uncertainty was part of it? So let's put our error bars on here. And again, I'm going to show you quickly today how to do that. Even there is a video up there, but I'll just point it out on Excel. So if these are my error bars, and actually we're going to have 2 ways like this, and I'm exaggerating the vertical. If you've already looked at this, as one of you mentioned, the mass error bars are going to be tiny, because our error is literally in the thousandth of a gram range on those, right, or hundredth of a gram. Whereas in volume, it's much larger error. So now I have this. What does that tell me?
Still not linear.
Well, first of all, let's realize that this actually makes a rectangle. And what this is telling us is that because of uncertainty in measurement, we don't know where in this rectangle the true value of the point actually was. In other words, the true mass. If we were omniscient, we would know that true mass and the true volume, presumably, to the gazillionth decimal place. And if we knew that, it would be somewhere in that box. But we don't know. So we just gave you the range. That's what the whole idea about saying plus or minus is. Our data was scattered within that range. We don't know which point, if any, that we took was true or was closest to the true value. That means it's possible that the true value was up in this corner of that range, right on the line. Same thing over here. It's possible that that true value is right on the line, and this one, and this one. How likely is it? That's something you could discuss. How likely is it that all four of the true values were actually right on that line? You can see that your confidence would grow as the average values were closer to the line. See what I'm saying? As the average points got closer to that line, your confidence in that conclusion would grow. But let's clarify it a little bit here. What we want to do is we want to put a condition on our hypothesis because we want to be as objective as possible, and ideally this would all happen before the experiment. You'd make a hypothesis like this, the relationship is linear, and then you would put a condition on it, something like this. We will accept this if none of the data are further than their uncertainty from the line. So, now why do we say that? I say none of the data are further. Let me draw one down here. So let's say that one of the data points was down here. Okay, good. So there's no chance that this true value was on the line. Another way of saying that is that this difference between the line and the data cannot be explained by random error. It cannot be explained by the measurement uncertainty. There must be another explanation. So this difference cannot be explained by measurement uncertainty. Remember, measurement uncertainty is inherent in the process of measurement. It's something we can't do anything about. We want to know about it. We want to estimate how large it is so that we can draw better conclusions. But this one is too large. It's something else is going on here. So let's add that. Something else must be going on. And that something else could well be that this is actually not a linear relationship. Okay? So the question here in the hypothesis, when you're looking at your hypothesis, the whole question is, can the deviations from the line, can the differences between your data and your hypothesis be explained by measurement uncertainty? If so, then your hypothesis might well be true. You with me? If the differences between your data and the hypothesis could be explained by measurement uncertainty, then your hypothesis might well be true. Because we expect them to be a little bit different, just based on measurement uncertainty. However, if the differences between your hypothesis and the data are larger than we expect due to measurement uncertainty, then something else is going on. And that something else is quite likely that your hypothesis is wrong. Do you follow me? So that's one way to approach it, and there's a second way that I'm going to show you in a second. Yes? I'm going to show you that too. So this is number one. Now there's a bit of a problem with number one that I'm not entirely comfortable with, and a lot of people aren't, and that's this. So let's say they do all touch the line. So let's put this one back on the line. So this is a linear relationship, definitely. Could it be anything else? Like what? Could it be a different kind of relationship? Is there another type of mathematical relationship that would fit these data? Sure, there's probably a whole bunch. For example, something like that, a nice wavy curve that goes up like that. Fits really nicely. Actually, that fits better than the line does. So we're accepting our hypothesis that it's linear? Yes, in this case, because we decided, what we did here in number one is we set up a decision criteria. And so here's the deal. To use the type of hypothesis that I just wrote in number one, you're going to use it when you have to make a decision. And so you're going to say, we are going to make this decision if these criteria hold true. We're just trying to make it more objective, so we're setting up these criteria. You follow me? And in science, this is sometimes done because they want to move forward, and so they set up criteria that are related to statistics. They're a little more sophisticated than this. You do a more sophisticated statistical test, but it's basically the same idea. Now, if you want to be more philosophically pure, okay, then here's what you do. You read this essay by this famous philosopher of science named Karl Popper. And Karl Popper, he wrote a famous essay called Conjectures and Refutations. He was tremendously influential in science. In fact, the way that people define science today is mostly because of Karl Popper. Conjectures and Refutations. And here's what he literally said. Science is all about making essentially guesses about what's going to happen or what's true about the world, and then trying to disprove them. Trying to disprove them. And so the conjecture is the hypothesis. And the refutation is the experiment. This is essentially a condensed form of the scientific method. This phrase, conjectures and refutations, is a very concise statement of the scientific method. I like it a lot better than the whole 5-step thing. Conjectures and refutations, that's simple. So you make a hypothesis and then you try and disprove it. But here's the main idea here. The main idea here is you can't ever prove your hypothesis, only disprove it. And there are some weaknesses to this, but I'm not going to go into that right now. We don't have time. So you can't really prove it, only disprove it. But I think you can get the gist of this from what I just said. In our discussion of this line, we were pretty darn confident when this point was, so let's draw this up here again. When we had something like this, and then one point was way down here, we were pretty confident that it was not linear. Okay? However, when they were on the line, or could have been on the line, we were much less confident that it was definitely linear, because we said it could have been something like that. So that's one way to look at this, is that it's easier to disprove than to prove. So you could approach your hypothesis in this way. Now, what would it look like if we did it like this? This is pretty challenging, but you guys can do it. What would my hypothesis look like if I was taking Karl Popper's approach? How would it be different than, let's look, I'll put this back up here.